And now I'd like to introduce our special guest for today. We're very delighted to have with us Dr. Fulvio Melia. He is the chairman of the physics department at the University of Arizona at Tucson, one of the centers of black hole physics. And he's the author of a new book called The Edge of Infinity, about black holes. So let's now get a few definitions off the ground before we head right into the center of a black hole. First of all, what is a black hole? Well, a black hole is an object whose escape velocity is the speed of light. In other words, light itself cannot escape a black hole. In other words, everything falls in, but nothing falls out. And then surrounding the black hole, there is a sphere called the event horizon. And the event horizon is the point of no return. If you fall through that imaginary sphere, you get sucked right into the black hole, and you never come out again. And lastly, we have two types of black holes. Stellar black holes, that is, old stars that peter out and collapse into a black hole, and galactic black holes, like at the center of the Milky Way galaxy itself, right in our own backyard. So once again, our special guest today is Dr. Fulvio Melia, and we are talking about one of the strangest objects in the universe, and that is the black hole. The first question for you is, how did you first get interested in physics and astronomy?
Well, I actually grew up in Melbourne, and I don't know if all of your listeners have had the opportunity of visiting the Southern Hemisphere, but looking up at the sky from the Southern Hemisphere, one gets quite a different view than from the Northern Hemisphere. The Milky Way, for example, is very easily seen, and it stretches from one horizon to the next, and it fills the cosmic vault. And when I was small, I remember almost every evening just going outdoors and just looking at the stars in the Milky Way for hours and hours and hours. And I would say that that's probably what started me off. With that, of course, comes the natural curiosity of how things work and what these objects are, and one is led, I think, in most cases, to a study of physics, and that's what got me into physics and astronomy, I would say.
And Arizona is one of the world's leading centers for astronomical research, I understand. So what is it like to be in Arizona versus being in New York City, to be able to look up at the night sky and see the Milky Way, and also to be at the very forefront of telescope technology?
Well, that's the interesting comparison, of course, because even though I usually tell my friends, especially the ones overseas, even though we belong to the same country, the southwest of the United States is really very, very different from the northeast, as I think everybody realizes. Here in Arizona, the skies are almost always clear. It's not a coincidence that many of the national and now the international telescope facilities are being built here. We get very little cloud cover during the year, so going out in the evenings, whether using a telescope or not, presents quite a glorious experience. It's a wonderful opportunity to feel the magnitude of the skies and the objects there. And of course, for research, especially for the observers and people who build instruments eventually placed on the telescopes with which these observations are made, there are very few places on the planet better than this to do studies such as this. The clarity of the skies and also the access to objects not only in the Northern Hemisphere, but those approaching what one would see from the Southern Hemisphere. Of course, Earth's rim prevents us from seeing all of the portion of the Milky Way that would be accessible from the south, but nonetheless, during a portion of the year, we could still see the center of the galaxy, for example, which is close to the southern horizon for us here in Arizona. But other than the skies here, the only other place that would present a comparable opportunity for studying these objects would be from countries such as Chile, which, of course, is way down south. So as far as we here in the United States are concerned, unless we want to travel to South America, this is probably the place to do this type of work.
And also, tell us a little bit about how stars die and the formation of black holes.
Right. Well, this, of course, is an ongoing investigation. We think we understand some pieces of the puzzle. Not everything is known. It's quite a long story. black holes can actually form in several ways, and it's not clear that the supermassive objects that we see in the nuclei of galaxies form through the stellar process of life and then death. They may have formed in other ways, and we may come back to this in a few moments when we talk about the genesis of these objects early on after the Big Bang. But in terms of the smaller black holes, like the ones like Cygnus X1, for example, the objects that we think weigh perhaps 10 to 20 times as much as the Sun, as far as these objects are concerned, most of them are produced when a very massive star, and by very massive would mean something, an object that weighs anywhere between 30 to 50 times the mass of the Sun, burns its nuclear fuel rather quickly, it turns out, because the more massive the object is, the faster it burns the fuel, and then eventually loses that internal support that prevents it from collapsing to the middle. It's the heat generated from nuclear burning that preserves the star during the main part of its life, like the Sun is now. And at the end, when that nuclear fuel is burned to heavier elements such as carbon and eventually to iron, the heat generation stops and the material can't support itself anymore and collapses into the middle, at which point a supernova explosion ensues, and the remnant, depending on how massive the original star was, can sometimes be a black hole with a mass somewhere between a couple of solar masses and 10 to 20, as I said earlier. So the vast majority of black holes about which we know, and there are some billion of these in the galaxy, probably formed in this way. But there is another class of objects, like the one at the center of our galaxy and the center of many other galaxies, such as the Andromeda galaxy, our sister galaxy. These objects have a mass anywhere between 1 million to several billion times the mass of the Sun. And although some of them may have started as seeds from supernova explosions a long, long time ago and eventually have grown to the point where they are now, it's not clear that all of them could have formed that way. And the reason I say that, and this would lead into another part of the story, the reason I say that is that we now have very, very strong evidence that at least some of these supermassive objects were formed only 700 million years after the Big Bang, much, much earlier than the formation of galaxies and much of the structure that we see in the universe today. So it's starting to look like there was some other mechanism, some other process that led to this early collapse and this catastrophic creation of very strong gravity surrounding these objects, which probably also then acted as nucleation sites that attracted other matter towards them, and that matter, we think, in many cases, may have led to the formation of galaxies. So the odd thing now is that we may actually owe our existence to the formation of these supermassive black holes, because they may have been the seeds that created galaxies, which then, of course, created stars within them and planets and life and so on. So it's quite a long, complex story, and we don't know all the details yet, but some of the pieces of the puzzle are starting to emerge in that there definitely appear to be several classes of these, and one class having to do with the supermassive objects somehow had a genesis much, much earlier than we thought before, and how they formed is not entirely clear yet.
Well, I have a question that many young people ask about black holes. First of all, black holes suck in everything. Even light itself cannot escape. In some sense, they're the ultimate roach hotel, and the Hubble Space Telescope has photographed the black holes eating up whole star systems. So in other words, things check into a black hole, but nothing ever checks out. Well, then the question is, well, a black hole should be invisible. Even light itself cannot escape from a black hole. Therefore, a black hole should be invisible. And yet we have the Hubble Space Telescope taking photographs of perhaps hundreds of black holes in outer space. And so then the question is, how do you photograph something that is invisible?
Right. This this is what's really generating much of the excitement these days with theoretical astrophysicists and, of course, the physics community in general. What telescopes that have been built up to this point have seen so far is not really the black hole itself, but what they see is light produced by matter falling into the black hole. Their resolution is not yet good enough for them to make an image of the black hole itself, the event horizon, which is the surface beyond which nothing can escape, including light. So if we really could see the black hole itself, what we would see is a dark shadow in front of a curtain of light. The curtain of light presumably would be produced by matter behind the black hole relative to us, and the black hole would absorb all of the light produced behind it or redirect it away from our line of sight, because gravity can bend the path of light, and so we would see a dark shadow. That's what a black hole would look like if we had a camera with such clarity, such spatial resolution that we could see detail down to that size. It does look like by the end of the decade we may have the capability of actually forming such an image. But for now, telescopes such as Hubble and Chandra have not been able to do that yet. So instead what they show us is images, or what they produce is images of matter falling into the black hole from larger distances much further away than the event horizon itself. Both have done spectacularly in this regard, though. Both Chandra, the X-ray telescope, and Hubble have each produced a very deep image of certain patches of the sky. By deep, we mean that there were patches in the sky, such as one in the constellation of Ursa Major, where there are very, very few objects within our own galaxy inside of that patch, and so it's like looking through a relatively open window to much distances much further away than objects within our galaxy. And what they were able to do by staring at these patches was to collect light from objects some 10 to 12 billion light years away. In other words, objects that were producing this light only 7 to 8, 900 million years after the Big Bang. And what they see when they look at these patches is very bright objects, either X-ray objects or ultraviolet or infrared objects in the case of Hubble, objects that number as many as 500 within a region only the size of the full moon. So if you can imagine with your eye looking at a part of the sky that has the size of the full moon, within such a region, these telescopes have been able to produce images of as many as 500 of these objects. And these objects are so far away, they're so bright, that the only way that they could produce this much light is if they're black holes absorbing matter from their environment and converting gravitational and rest mass energy into light. So we believe that when we look at these patches, most of the objects that we see, most of the 500, must be supermassive black holes at that distance in the universe. And what's interesting is that when one extrapolates over the whole sky, these numbers correspond to total numbers of some 300 to 400 million such objects. And we know that that's not all that's there, because that's what we can count. That's what we can see. But some of these objects are probably also obscured by dusty matter falling in towards them, and so it's not clear that we're seeing everything. So the best that we can say is that there must be at least 300 million of these supermassive black holes spread throughout the cosmos. Chandra, of course, has gone on and done even much better than that. It's allowed us to look at the supermassive black hole at the center of our own galaxy with even better clarity because it's much closer than the others. It's only 25,000 light years away compared to the 12 billion light years of many of these other objects near the beginning of the universe's life. And because this object at the center of our galaxy is so close, we've been able to study it with Chandra and now other instruments as well. The European Space Agency has its own X-ray telescope called XMM Newton, which has done similarly spectacular studies of these objects. But with Chandra, we've been able to see the X-rays produced by the black hole at the center of our galaxy with enough resolution that we can actually place the source, the location of the emitting plasma, within a region no bigger than the distance between the Earth and the Sun. In addition, this object seems to explode roughly once a day, producing a flare of X-rays. The X-ray intensity during these events goes up by anywhere between 30 and 200 times what the intensity is during the quiescent state. And so for a couple of hours, the black hole at the center of our galaxy shines much, much brighter than it otherwise does. And what's intriguing now, and these are the latest results that haven't even been published in the literature, what's intriguing now is that there is very clear evidence that during these events, we can see a periodic pulse. It's like the heartbeat of this object. It's a periodic pulse that occurs roughly once every 20 minutes. The natural interpretation for this, and again, it hasn't been published yet, so we have to look at this more carefully and make sure that we've ruled out all the other possibilities. But the natural interpretation is that what we're looking at is a phenomenon associated with X-rays being produced in a region orbiting the black hole within a distance only 3 to 4 times the size of the event horizon. So although we can't see the event horizon just yet with Chandra or Hubble, nonetheless, we're seeing a phenomenon associated with emission that's occurring only 2 to 3 times the size of the event horizon. It's similar to what would happen if you imagine putting a searchlight on a planet and being in its focal cone only when the searchlight is pointing towards you. And so you would see a pulse every time the planet goes around the sun, which would then lead to a periodicity or a period of 1 year in the case of the Earth, because that's how long it takes the Earth to go around the sun. So it's a similar phenomenon with the black hole at the galactic center. We see this pulsation roughly every 20 minutes, and so we interpret that as being part of the plasma in orbit around the black hole, and the distance that corresponds to that period is about 3 times the size of the event horizon. So these are some of the most exciting things that are happening now as we speak, and the prospects will get only better as time passes and Chandra and XMM continue to look and discover additional activity, and also with the next generation of telescopes in the pipeline now.
Now, everyone asks the question, what happens if you fall into a black hole? No one's ever done that, of course. But could you explain some of the distortions of space-time that occur if you were to fall into a black hole and someone were to observe you falling into a black hole from a distant planet?
Right. And the answer to that, of course, depends, not surprisingly, on how massive the black hole is. What one would see falling through the event horizon differs depending on how massive the black hole is compared to the mass of the object or the body falling in. It turns out that for a massive object like the one at the galactic center, which we now understand has roughly 3 million solar masses worth of material contained within it, falling through the event horizon of an object like that, a person would actually not see very much, would actually not feel very strong effects on his or her body. There would be other distortions to the light, but we'll come back to that in a moment. The point is that what happens physically to matter falling through the event horizon depends on how big the object falling in is compared to how big the event horizon is. And the size of the event horizon scales with the mass of the black hole. So, for example, if the sun were to shrink down to the size of a black hole, its event horizon would have a radius of only 3 kilometers, smaller than a city. Whereas the black hole at the galactic center has an event horizon with a radius about 1/20th the distance between the Earth and the Sun, which is much, much bigger, of course, than 3 kilometers. And it's the difference or the comparison between the size of the event horizon and the size of the object falling in that determines how much physical damage, if we can put it that way, is done to the object falling in. So because our body is so small compared to the size of the event horizon of the black hole, the galactic center, we could fall right through and not feel very much physical damage. We wouldn't get distorted or pulled or stretched or compressed. We would be able to pass through the event horizon, and then other catastrophic events would ensue, I'm sure, after that. But the process of falling in wouldn't do damage to us. On the other hand, if we were to fall through a smaller black hole, like the Sun, again, if the Sun were to be compressed to 3 kilometer size, then our body would get stretched at first, pulled apart, and catastrophic damage would follow. We would be disintegrated, and only the atoms and molecules would fall through. So the physical damage is different depending on the size. And a good analogy would be compare standing on the surface of the Earth, where the surface of the Earth, even though it's spherical, looks flat to us because it's so much bigger than us, and then standing on the dome of a cathedral. The dome is quasi-spherical at the top, but because the size of the sphere is much smaller compared to the Earth and much closer to our size, we feel the curvature of the dome much more. And so that's the analogy. A small black hole, because of its greater curvature relative to us, would do more damage to our body falling through than a big black hole does. Now, that's as far as physical damage is concerned. But what we see, though, would be less dependent on the size, and there would be significant distortion to the light path progressively as we get closer and closer to the event horizon. So light, because of gravitational redshift, meaning that photons have progressively less and less energy, not speed. The speed of light is always the same, but the energy of the photons decreases relative to us at infinity as they get closer and closer to the event horizon. Because of that decreasing energy, we have greater and greater difficulty seeing the light. Eventually, as the light reaches the event horizon, it's lost all of its energy relative to what we see, and so we wouldn't be able to even detect the light anymore, even though it would still be coming out until it passes through the event horizon, and then beyond that we wouldn't see it anymore. But as we fall in, because of this effect, we would tend to see primarily light concentrated closer and closer to the zenith angle, right above our head. So as we get closer to the event horizon, we see a progressively smaller cone of light from the rest of the universe until that point when we cross the event horizon itself, and only the light coming directly down would be visible to us. And so we would see these significant distortions because of the light bending and the gravitational redshift. And when we cross the event horizon, then of course nothing can go back out, so we can't communicate with the outside world, but what we would see is only light falling directly inwards towards us.
Well, I'm afraid that's it for the first part of Exploration. Once again, our first special guest was Professor Fulvia Melia, Professor of Astronomy at the University of Arizona. And in the second half, we bring on Professor Richard Gott of Princeton University, who is the creator of his own version of a time machine. Welcome back to Exploration. Once again, this is Dr. Michio Kaku, Professor of Theoretical Physics at the City College and the Graduate Center of the City University of New York And this is the second half of Exploration. In the first half of Exploration, we begin a discussion with Dr. Fulvio Melia. He is a professor of astronomy at the University of Arizona and one of the leading experts on black hole physics. And as you said before, black holes are not science fiction. We see these things in outer space. They gobble up entire star systems, but then that leaves open the question, well, if black holes can eat up entire star systems, where do the stars go? Well, to be blunt about it, we physicists don't really know. There's a controversy among physicists as to what happens. Some people think that stars are simply crushed into nothingness and, well, that's it. Period. End of story. The black hole has just had lunch. Other people say, well, not so fast. Perhaps black holes can be gateways to another universe. And then the question is, well, what lies on the other end of that universe? And again, we're now entering the realm of science fiction because Einstein's equations break down. They break down at the two most interesting points in space and time. First, the center of a black hole. Einstein's equations are useless at that point. Einstein's equations do predict that black holes might be used as time machines or gateways to other universes, but these equations are unreliable because the gravitational force at the center of a black hole becomes infinite, and that's nonsense. It just means that Einstein's equations are incomplete. The second place where Einstein's equations break down is the center of the Big Bang. Another very interesting place. We simply don't know what happened before the Big Bang. Well, now we have something called string theory, which is what I do for a living. That's my day job. And in principle, we might be able to answer these questions of what happens if you go through a black hole or what happens if you go before the Big Bang. And string theory seems to indicate that if our universe is a bubble of some sort, then there are perhaps other bubble universes out there that are also expanding. And if these bubble universes collide, or if these bubble universes peel off a baby universe, then perhaps that's the Big Bang. So it's fair game now to ask what happened before the Big Bang. But what about time travel? Well, again, we have to rely on string theory. String theory is not advanced enough to answer that question. But if time is a river, as Einstein said, then that leaves open the possibility that the river of time could have whirlpools. And if the river of time has whirlpools, these are called closed time-like loops, and it allows you to leave, let's say, your office, and come back before you left. In other words, you might be able to come back yesterday. Now, this, of course, is all nonsense, you might say to yourself, but hey, these are logical conclusions of Einstein's equations and perhaps may even be allowed by string theory. So our next guest is Dr. Richard Gott of Princeton talking about time travel. And now I'd like to introduce our very special guest today. Once again, we have with us Professor J. Richard Gott III. He's a professor at Princeton University, and he's the author of a book called Time Travel in Einstein's Universe: The Physical Possibilities of Travel Through Time. Now, just remember that we're not talking about some inventor in a laboratory in his basement creating a time machine by which you can erase certain rather embarrassing events in your history. We are, in fact, talking about hard physics. We're talking about perhaps one day a civilization much more advanced than ours, or perhaps maybe even our descendants thousands of years from now, may have the ability to manipulate the energy of a star, in which case they may be able to create a time machine capable of changing the past. And so the question is time travel possible, given the fact that there are all sorts of horrible paradoxes you can get if you go backwards in time, for example, and shoot your parents before you're born? So, once again, today our guest is Professor J. Richard Gott III, a professor at Princeton University, and we are talking about time machines and time travel. The first question for you, Professor Gott, is how did you first get interested in physics?
Well, I got interested in astronomy when I was about 8 years old. I belonged to a stargazer group that was organized by our junior astronomical society, and so I had a telescope, and astronomy was a hobby of mine in high school. And when I became interested in physics in high school and so forth, I later decided to take my physics and work on astrophysics because that had always been a hobby and of particular interest to me.
And was there anything about the romance of the stars? Anything about, for example, looking for intelligent life in outer space or wondering where the universe came from? Was there anything specific about astronomy that fascinated you?
Well, I was particularly interested in the Big Bang theory. At that time, this was a bit before Penzias and Wilson had discovered the cosmic microwave background radiation. So I was always a fan of the Big Bang theory versus as opposed to the steady state theory.
Okay. And I understand today you're affiliated with the Intel Science Talent Search, or formerly known as the Westinghouse Science Talent Search. So tell us a little bit about your experience judging high school kids.
Well, for many years I was the chairman of the judges for the first Westinghouse, and then it's now sponsored by Intel, the Intel Science Talent Search. And this is a wonderful science competition. It's the oldest and most prestigious competition for high school students in science in the country. And 5 of its winners have gone on to win Nobel Prizes. So it's a wonderful contest, and it asks you to do a piece of real research and submit your research just like you would write a research paper and so forth. So unlike a test of some sort, it's really you just try research, and we look at your research. So it's kind of like if you were a baseball camp, you could test people out by seeing how fast they ran down to first base. That would give you some idea of how they might play baseball. But a baseball scout would tell you that it's really, if you're scouting for the major leagues, you really want to see people actually play baseball. So this gives students a chance to do real research projects, which are fun. And many people that enter this contest, they fall in love with doing research and do it for the rest of their lives. And many of the winners of this contest have gone on to wonderful careers in science. So I would encourage people to apply for it. 40 winners come to Washington each year, and they give out very large college scholarships, and it's a very exciting thing.
Okay, now let's talk about time travel in particular. There's a movie hitting the silver screen right now called Terminator 3, where killer robots from the future come back to harass us in the past. So what started your romance with time machines? Because in the area of physics, most physicists tend to, at least in the old days, scoff at the whole notion of going backwards in time.
Well, I got interested in time travel by exploring some solutions to Einstein's equations. Einstein developed his theory of general relativity, which is his theory of curved space-time to explain gravity. And we take this theory very seriously because when he finally solved the equations for this in 1915, they made predictions about light bending as it would pass near the sun, and these were checked experimentally, and Einstein was found to be right and Newton was found to be wrong. So since then, people have been interested in exploring exact solutions to Einstein's equations, and you've heard of probably the most famous one is the black hole solution. That's an exact solution to Einstein's equations. So we take black holes seriously, even though they're quite extraordinary objects, because they do solve Einstein's equations of gravity. So I got interested in cosmic strings. These are theoretical objects that are dense threads of energy left over after the Big Bang that are predicted in about half the theories of unified particle physics in the early universe. We haven't found them yet, but we are searching for them. And I found an exact solution for one cosmic string, what the geometry around one cosmic string would look like. And William Hiscock found the same solution independently of me, so we're given joint credit for this solution to Einstein's equations. And then later, I investigated two moving cosmic strings, what an exact solution would look like if two strings were to pass each other. And I indeed found an exact solution for that geometry. And it turned out that if the strings were moving fast enough but still slower than the speed of light, that this was a solution that would allow you to circle around the cosmic strings and arrive back home before you started. So it would allow time travel to the past. And there have been a number of general relativity solutions like this. The first one was found by famous mathematician Kurt Gödel in 1949. It's a rotating universe that we don't live in that kind of universe, but it's an interesting solution to the equations that allows time travel to the past. And if there's one solution like that, there could be others. And then Kip Thorne and his associates found wormhole solutions that allowed time travel to the past. So it's extremely interesting that these equations of Einstein's of general relativity themselves, and this is our best theory of gravity at the time, seem to allow solutions that allow time travel to the past. So I got interested in it just from trying to understand Einstein's equations with objects that we were interested in.
Okay, now let's talk about the movies. Everyone likes the movies, and people have seen a lot of movies where we have black holes that are rotating very rapidly.
Right.
And according to mathematician Roy Kerr in 1963, he did find a solution of Einstein's equations where if you pass through the ring, not a point, but a ring that's spinning very rapidly, you would wind up on a parallel universe, perhaps even in a distant point in time. So could you elaborate about what happens if you, heaven forbid, fall through a black hole and make it, quote, to the other side, unquote?
Well, this was an unperturbed black hole. It's a solution to Einstein's equations, and this is one that's left alone completely, and you ignore the effects of Hawking radiation, which we can mention later. But this first solution for a rotating black hole showed that if you traveled inside the black hole, instead of a singular point in the center, you would find, as you said, a ring singularity. If you passed through the ring, you could navigate your spaceship in such a way that you could travel back in time. And then after leaving this region, you could go and pop out into another universe, sort of like getting on an elevator at a store and going up to the first, going from the first floor to the second, and you could get out on the second floor universe. Then later you could go out and go up to a third floor universe and so forth. But there was no getting back to the first floor. Once you went in the rotating black hole, it was not possible to come back outside and brag to your friends about your adventures. But quite interestingly, there was a region of time travel that was trapped inside the rotating black hole in Kerr's solution.
Okay, now let's say you go through the black hole and you're not crushed by gravity because it's, gravity is spread out a little bit throughout the ring. However, there are some naysayers who say, wait a minute, let's not go so fast. And you mentioned that the black hole was not perturbed. So could you tell us a little bit about some of the naysayers who say that maybe you can't make it quite all the way through that black hole?
Well, the trouble is that when you pass inside this black hole and you pass into the region of time travel, if you're looking back outside, you're seeing the history of the external universe as you're passing outside. And in Mr. Kerr's solution, as you passed into the region of time travel, you would be able to see the entire future history of the universe pass before your eyes. Now, you might say, well, this is a good thing, very interesting for historians. You get to see the whole future history of the universe in a finite amount of time. But the trouble is those photons coming in would be infinitely blue shifted and become, instead of visible photons, they would become ultraviolet and gamma ray photons. So these could kill you. You have to pass them on your way into the region of time travel. Other effects need to be considered, too, like the fact that the black hole may evaporate, would it be expected to evaporate from Hawking radiation, which cuts off your view of the very late history of the universe, but also induces other effects, quantum effects on the inside of the black hole. So the situation is that some people have explored this situation, Mr. Burko for one, Amos Ori, and they have found that you traveling to the region of time travel, you would probably pass a singularity. The curvature of space-time would become infinite. However, it takes a very brief amount of time for this to occur, so the singularity may be weak in the sense that it may not tear your body completely apart. And also, quantum effects would be expected to knock out any infinities in the solution. So the trouble is that we don't really know exactly what happens to you when you go inside a rotating black hole, and we may need a theory of quantum gravity to explain this. We know how gravity behaves on macroscopic, ordinary scales. Einstein's theory gives us a wonderful and very well-checked theory of that, but we don't know how gravity behaves on microscopic scales, and to understand what would really happen going into a black hole, we may need to know that.
Okay, well, we have had on this radio show several people who work in superstring theory, like I do, and we do look at these things. However, the theory is not very well developed yet. So let's ask a hypothetical question. Let's say you are an advanced civilization, like we see in the movies. An advanced civilization that can move planets and move stars. I mean, really powerful technology we're having here now.
Yeah.
With that kind of technology, do you think that someone could go through the ring to perhaps a parallel universe or perhaps in time, or it's just simply not known in terms of what we know about quantum gravity? Or do most people think, bah, humbug, you just can't do it?
Well, I think that if you were using my cosmic strings, what a super civilization would try to do is find a loop of cosmic strings. Cosmic strings either infinite, they have no end, so either they're infinite if we found them. They're either infinite or they come in loops. So you can think of spaghetti or spaghettios. So find one of the spaghettios, one of the loops, manipulate it so that it collapses by a large factor. And you could arrange it with your massive spaceship flying around it so that the two sides of the string would pass each other at the speed required to make a time machine. But I was able to show in that case that this would also be in grave danger of forming a black hole. In fact, it would likely form a black hole. So the regions of time travel would likely be trapped inside, just as we've talked about in the rotating black hole case. So I think one thing to emphasize is that these are projects that really, this loop would weigh half the mass of our own galaxy. So we're talking about projects that really only a super civilization could attempt. But as you say, we're interested in finding out whether a civilization with arbitrarily large powers, but still operating under the laws of physics could do it. And I think probably until we really get a theory of quantum gravity, we can't say for sure whether they would succeed or not.
Okay, now let's talk about the wormhole, because on Star Trek, they simply zap through wormholes to the other side of the galaxy. Now, if you had a black hole, there is a problem there, and that is it's a one-way ticket. It's basically a roach motel. You go in and you never check out again. It's a one-way trip. However, these wormholes that we see on Star Trek are transversible. You go back and forth, back and forth. It's like taking a Sunday drive right through a wormhole. So tell us a little bit about wormholes and whether or not they're practical.
Well, the wormhole idea got started when Carl Sagan, who was writing this book Contact, which later became a famous movie, he wanted to use a wormhole to get Jodie Foster from one part of the galaxy to another. And so he called up his friend Kip Thorne and said, listen, I'd like to get the physics right here. What about the physics of wormholes? So Kip Thorne and his associates investigated this, and they found out that in order to transverse it back and forth, you had to prop it open with some what we call negative energy density stuff. This is stuff that weighs less than zero. In other words, you'd have to add mass to this to get back to zero. It's stuff that weighs less than zero. Well, that's very strange stuff, but You might say, well, that's strange. You wouldn't expect to find that. But curiously, we do know of a quantum mechanical effect, the Casimir effect, which is one where if you take two parallel metal conducting plates and you put them very close together, the quantum vacuum state in between the two plates actually acquires a negative energy density. It weighs less than zero. So Kip Thorne was proposing, and similar effects occur in connected with Hawking radiation and black holes and so forth. So we know of quantum effects that can induce negative energy density states. So what Kip Thorne proposed to do was to cover the mouth of each wormhole with a conducting plate and put them close to each other in the wormhole tunnel, 10 to the minus 10 centimeters apart, so that they introduced a large negative energy density. And then you could traverse, by opening trapdoors in these metal plates, you could traverse the wormhole and not be killed. Again, the engineering effects of this were enormous. The wormhole he was talking about involved 200 million solar masses, 200 million times the mass of the sun. So, but again, he was interested to know whether these things were possible in principle at all under the laws of general relativity.
Okay, well, let's say you want to build one of these things, okay? People talk about these things. Paul Davies, who we actually had on the radio show a few years ago, even wrote a book about how to build a time machine, okay?
Sure.
Now, again, one of the problems is you have to get negative energy if you go the route of the wormhole. And then the question is, well, how do you get negative energy in large quantities? The Casimir effect is very tiny. It takes laboratory instruments, very delicate instruments, to measure this effect. However, we want to just rip space and time apart and change the topology of the universe. So if you were, once again, a very advanced civilization, how could you possibly assemble large quantities of negative energy to open up a wormhole?
Well, the mechanism that's being used is to bring the plates very close together. The plates are pulling you toward each other. This effect has been measured in the lab, and if you let the plates go very close to each other, you can get a very large amount of negative energy density. You have to engineer this so that the plates can go. In Kip Thorne's case, he was having them 10 to the 10th centimeters, 10 to the minus 10 centimeters apart. So that's the mechanism that's used. How do you get the wormhole in the first place? The idea here was that space-time on very small scales, 10 to the minus 33 centimeters, microscopic scales, may be sponge-like. The quantum fluctuations might be causing little microscopic wormholes to be forming all the time. And so the idea would be to find one of those and somehow enlarge it. This was Thorne's proposal. And make it large enough so and then you could keep propping it open with this negative energy density stuff. So no doubt it's an extraordinarily difficult feat, but we're interested to know whether it's possible in principle.
Okay, well, there's even a television commercial now I was watching talking about building a wormhole to deliver products to the customers. So the idea of wormholes is out there. However, the advertisement stumbles on this whole question of, well, how do you energize this thing with negative energy? So you mentioned the Casimir effect. Where else in the universe can we find negative energy? It's a very exotic kind of thing. It's not the kind of thing we see in the laboratory. Where else in the universe can we find negative energy?
Well, black holes is one location. When Stephen Hawking was working on black holes, one of the things he proved was that if once you formed a black hole, it would only get bigger. Its horizon, as it were, would only get bigger. And so as it gobbled more and more material, in fact, he proved a theorem that if energy density was always positive, the black hole, if you just add energy density to it, the black hole would always get bigger. But then people started to think about what would happen to a black hole with quantum effects, and Stephen Hawking showed that black holes actually evaporate. And so over time, there's a quantum vacuum effect in the empty space around the black hole that you have vacuum fluctuations that cause particles to be emitted from the black hole and then also cause the black hole to lose energy. And so if you look at the quantum vacuum state that exists around the black hole, which Stephen Hawking found, it has a slight negative energy density which steals energy from the black hole and causes it to evaporate. And so that's an example of a naturally occurring phenomena that we expect is occurring every day.
Now, Paul Davies, in his book on how to build a time machine, stumbles over this very same question, and he mumbles that, well, maybe we can build banks of laser beams. Lasers can have positive and negative what are called squeeze states, and he doesn't explain how to do it. And this is, of course, the key question. What is the gasoline? What is the energy that drives your machine? And he mumbles and says, well, maybe one day we'll have huge banks of lasers that we could fire into our chamber to prop open the mouth of a wormhole. Are you impressed by that book?
Well, I probably wouldn't use lasers. I mean, I still think the Casimir effect that Thorne talked about is the most promising proposal to get the negative energy density state. We know it produces a negative energy density state, and the engineering question is, can you build these plates, close enough together? This is a extraordinarily challenging engineering solution. But he was going to do this by having electrically charged plates. The electric charge would keep the plate from collapsing. The repulsion of the electric charges would keep the plate from collapsing, and to put the two plates very close together. So I think that's the original Kip Thorne and his associates proposal is still the most if you will, practical one, and this is really something that we've observed in the lab. So I think it's by that turn, they were trying for a conservative solution that involves physics that we understand.